If you use a multimeter to measure AC voltage, then you'll see a single number pop up on the meter. But an AC signal continuously goes up and down. So what is this single number that shows up? In this video, we'll talk about the RMS value, the way to calculate it, and the reason it is significant. There's also a challenge question at the end, so make sure to watch the full video. Come on, you've got the attention span. RMS stands for root mean square. It is a type of average that scientists really like to use. And yes, I said scientists, not electrical engineers, because the RMS value is not specific to voltages and currents. You see, the RMS value is of interest in many scientific applications. For example, the average kinetic energy of any single molecule in a sample of gas is proportional to the temperature in kelvins, and this is governed by the following equation. This term over here is closely related to the RMS speed of the molecules. And speaking of the RMS speed, let's go through a quick example to give you a better feel for the RMS and why it's used. Let's say we have these 5 molecules of atmospheric nitrogen moving at different speeds. If we want to find the RMS speed, then we take these 5 numbers, square them, and then find the mean of the squares. Then we take the square root of this result, and that will be the RMS speed. In this case, the RMS speed of the 5 molecules is approximately 514 meters per second. And we can see that it does a very good job at representing these variations with a single number. Now you may be thinking, the normal average has the same effect. If we were to find the arithmetic mean, we would get 514.2, and that's very close to the RMS. Well, yes, but the RMS value has a distinct advantage over the arithmetic mean. It's insensitive to negative values. There is no such thing as negative speed, because we're talking about speed here, not velocity. But hypothetically, if we were to assume that the 4th molecule were moving at a negative speed, then the RMS would remain unchanged. The negative value would be eliminated by the squaring that happens. But the arithmetic mean, on the other hand, would be dealt a massive blow, falling all the way down to 296. So, in situations where we're primarily concerned with the strength of the numbers, irrespective of the sign they hold, then the RMS is a much more useful tool than the regular mean. And that's particularly the case with voltages and currents, because AC waveforms typically have positive as well as negative values. So if we were to find the arithmetic mean of a single cycle, then we would get 0, because there are positive numbers and negative numbers with the same strength. So we square the waveform, taking the average to a positive number. But then we have to take the square root to undo this squaring that we did. And this result will be the RMS value of the original voltage waveform. So we now know what the RMS value is. But how do we calculate it? We saw an example with discrete numbers. But how do we deal with continuous functions like voltage and current? This is the formula. VRMS is the root of the mean of the squared voltage. Nearly all electric energy in the world is supplied by sinusoidal voltages and currents. So we can express V as the most general sinusoid. We can give it an amplitude Vm, which stands for V maximum, and then we'll have a general cosine with a certain radial frequency and a certain phase shift phi. V squared would be Vm squared cosine squared. Substituting this, we get the following expression for VRMS. Now, for the mean, we're taking an integral over one period, and then we're dividing by the length of that period. But T naught here is arbitrary. It doesn't matter where we start as long as we span one period and then we divide by that period. So let's go with the easiest option of setting T naught equals 0. Let's also worry about the square root at the very end. Now, Vm squared is a constant, so we can take it outside. And to integrate cosine squared, we're going to have to use the double angle identity. Solving for cosine squared, we get this expression. So we're going to have to substitute this into the integral. Now, let's take the 1/2 outside and then split the integral of the sum we have. So we have the integral of cosine 2 omega t plus phi, and then the integral of 1 dt. Notice that this cosine has double the frequency, so it has half the period. And we're integrating it from 0 to t, so we're integrating a cosine over 2 periods. The integral of any sinusoid over an integer multiple of its period is 0. So this integral will vanish. You can verify it yourself by finding the antiderivative and plugging in the bounds, but you will get 0. We are left with this integral of 1 dt, and that's of course t. The t and t cancel out, and VRMS becomes Vm over the square root of 2. So there you have it. This is a general formula for finding the RMS voltage if you have the peak value. Just divide by the square root of 2. And the same thing applies for the current as well. So we now know what the RMS value is and how to calculate it. But what makes it this significant in the eyes of electrical engineers? If we were to take a DC source and use it to power a certain resistance R, then the power delivered to the resistor would be Vs squared over R, where Vs is the constant DC voltage. Now, if we were to use an AC source instead, then the power would also be given by Vs squared over R. The only difference is the voltage here is changing. So the power is a function of time. It's called the instantaneous power. But if we wanted to find the average power delivered to the resistor, then this would be called the active power to distinguish it from reactive power and apparent power. Perhaps this is a discussion that we'll leave out for a separate video about the types of power in AC circuits. But this is basically the real power that you pay money for in residential use. If we were to find this power, what constant value for the voltage should we put in the numerator? You guessed it. It's the RMS voltage. Now, to cement your understanding of the equivalence between these two setups, let's consider a small example with numbers. Say the resistance is 50 ohms in each case. Then the power would be 200 watts in each case. Now, if we consider a time period of 10 seconds, then the energy delivered to the 50 ohm resistor is 2000 joules for both circuits. So, the AC source is identical to the DC source in terms of energy delivery, provided that the RMS value is equivalent to the DC value. For this reason, the RMS value is also called the effective value, and the two names are used interchangeably. The effective value is so widespread that equipment ratings for voltage and current are usually specified using the RMS. For example, say we have this light bulb with the following nameplate specifying the voltage and power ratings. Then this voltage is the RMS value at which the light bulb best operates. it's implied that this is the RMS and not the peak of the AC voltage, because the effective value is so widely used. Now, here's the challenge question I promised. What would be the peak current of this lamp? Not the RMS value, but the peak, the maximum value of the current sinusoid. Give it a think and let me know your answer in the comments down below.